Welcome, everybody. Glad to see everybody here. And I will talk about our model integration of solid material into the CSM model. First, I want to introduce the people that are here from our team, which is, besides me, Christina, who's over there. You want to stand up. And Ilaria and Kwesi. So if you have any questions in their work, I'm showing. And so also thanks a lot to all the collaborators that really supported us, listed here in getting this going. Lots of support by Sandro and others to help. We have mostly thought about, when we run our model, CSM, we have injected, we did a lot of model studies with sulfur injection, stratospheric aerosol work, volcanoes, so mostly sulfate. But we have not integrated solid material before for looking at stratospheric aerosol injection. So this project really allows us to go and dive into this. And so this is more a first results on those experiments we have been doing, and hopefully, so really preliminary results. So I do want to introduce the model we are using, the aerosol model, which is the CARMA model, and then focus a bit of the time on our initial results to implement it in our global model and see how that compares to other results from the SOCAL model. And we also have this CARMA box model that we did some preliminary box model studies by Ilaria. And I do want to briefly also touch on work that Kwesi is doing on dynamical downscaling with CSM to look at impacts over Africa. And then talk about conclusion and next steps. So CARMA is a sectional aerosol model, but it's also suited for clouds. Here we're using it for aerosols. It really describes the aerosol distribution in the atmosphere in terms of bins. We can choose how many bins. We describe different aerosols. We can divide into groups of aerosols that are internally mixed and so on. All the microphysical processes that we know on the physical equations are included, like the nucleation. That's important for sulfur because sulfates are produced by nucleation initially from sulfur in the stratosphere. But then also coagulation is really important. We see for the proctal particles and so on, sedimentation, how do the particles fall out. We can in this model consider spheres as well as fractals, and we can also include removal like wet and dry removal. This model can be run as a column model, being like a box in the atmosphere that can change. A box model or a column model, thinking about radiation if we want to understand radiative properties. But it also is integrated in several system models by now. And here we show the integration in CSM. It's publicly available via GitHub. And right now we're working on also some very easily accessible Python scripts that are available very soon because we port them in a new model version. I will talk about the model results that when we implement CARMA into CSM. And as I said, CESM has been used for several SAI, stratospheric aerosol injection studies in the past. This is really a system model connecting the atmosphere, the land, the oceans, and so on. And the atmospheric model can be run in different configurations. What we are using is the high top model configuration, also WACAM, that goes up to 140 kilometers, since we really want to simulate the dynamics in the stratosphere. Well, we do have comprehensive chemistry, and for this model version, we use especially stratospheric chemistry. And then, of course, we have interaction with the land and surfaces, and can run it as a free-running model, free-running meteorology, or some nudged meteorology, as you will see. And the model horizontal resolution is 2 degrees. So the CSM integration we have done before. It uses really the description. We were replacing aerosols with this CARMA model, with the sectional aerosol model, because the default model is a model. As you can, for example, see, the atmosphere can be represented through modes, the aerosols in the atmosphere. And here we really do this to the sectional aerosol model. We have different groups initially, mixed aerosols and pure sulfate group, and what we will do is we add these other solid materials to this We have evaluated the model a lot. Ilaria, for example, has done a lot of evaluation with volcanic eruptions, Sunga Tonga or Mount Pinatubo, and also used it, as I said, for stratospheric aerosol injections. And so Sandro and their team had done a lot of work in the past with the so-called model in implementing the aerosols, alumina, calcite. It's really complicated, and so we had to start from the beginning. And where we start is we want to go through these steps, and I show some initial results, as I said. The first, we implementing the solid material, which is alumina, calcite, and diamond. And first of all, we implemented with the CARMA model so we can transport it, we can interact with radiation and heating, but we so far in this first step haven't coupled it to chemical changes yet. And it doesn't really coagulate with other materials other than itself. So it's an independent aerosol. The second step then is that we, starting with alumina, and I show some results, we do interact alumina with sulfate, with the sulfate group, so it can be coated, and we can look at heterogeneous chemistry, and we can look at the effects on ozone. And then the next step will be to run this all together in some model simulations. So here are the first results. We add alumina, as I said, calcite and diamond, 3 different model simulations. And then we also have a model simulation without any aerosols. We run it for 5 years. We take most of the description that are described by Sandro's papers and Sokol because we really want to try to first represent and reproduce what has been done in a different model to compare it. We take optical properties, and John Dykema gave us really high-resolution optical properties for us to use. We can use the MECO to simulate that. And then our experiments is similar to what Sandro has done before, injecting 5 teragram of material in a band around the equator, 50 north to south, and around 21 kilometer altitude. And so, yeah, for the initial experiments, we do fix the sea surface temperature, but we have a free running atmosphere, so we can look at changes in temperature and radiation and so on. So here is some initial results. So when you think about when we include this aerosol into the CARMA model, we have these different bins, as I said. And every bin will differ in mass, and it will basically double the mass from one to the next bin. So the first bin, when we inject, is the monomer. It's the size that is the optimal size, or whatever size we say the monomer should be. In this case, it is 215 nanometer of alumina. And then, of course, the model will experience coagulation. So the next bin is then the dimer, and then it's doubling again, and so on. So you see the mass is basically falling off. Most of the mass is for all these injections staying in the monomer, which we want, because what we saw in the first talk, that's the best for the radiative shortwave forcing. If we go to larger agglomerates, the radiative forcing goes down. And so we can test this, and we can compare, look at the total mass, summing up all those different bins. And so here you see already alumina has a certain amount, calcite is a little larger, diamond changes a bit. We see that we do actually have much more mass in higher bins here. So the mass does not stay in the monomer, which would be desired. On the right is also we change some of the size of aluminite because we do implementation with the sulfate, as I said, the sulfate coating. And that was done by Sandro in a different size initially than the radiative forcing experiment. So we try to be consistent there. But you already see that it matters when you change the size. You do change the distribution. When you coat particles, you also change that, which is, I think, consistent. Yes?
Can you just clarify?
Yeah.
Sorry, can you just clarify are you assuming certain rates that are material dependent for the aggregation? And in this, or are these inputs that you're assuming? And is it over time? I'm confused.
Okay, yeah. So we are injecting monomers in a certain size. We assume certain properties of the particles. That means the fractal dimension of the particle. And so just that, we put in our aerosol model, inject a certain amount in a certain place, right, in that tropical region, and then the aerosol will evolve. It will get transported and infected. And then here, what you see, for example, is that you get a certain size distribution, right? And after some time, from the monomer, the particles coagulate by itself through the aerosol microphysics, through coagulation. So we're not prescribing any of that. It just happens through the aerosol microphysics that we get this distribution. And so what I showed here was actually just here at 25 hectopascal, some area to look at the size distribution. How do the aerosol look like? Does that make sense?
And so the bins that you show on the next slide are after the 5 years?
Yes, after the 5 years, the size distribution. Yeah, I will actually show something for the initial formation using that box model, how that looks like in a little bit too, if there's time, hopefully. And so we compare this to what Sandro had done. So basically, this is the same plot. It just shows here alumina and then the monomer dimer, and so summed up in mass. And I do that because Sandro did the same plot here. And what you can see already in these two different models is that in this model, we have actually much more mass than what they had for about the same model experiments. This is alumina compared to these, and then calcite is a little higher, and this is diamond. We do agree that basically we do have more agglomerate distribution for diamond, but it is more mass and it is higher. So that means our model will be already less effective in the shortwave radiation. And that will be shown in the next slide soon. So first I show stratospheric aerosol optical depth after the 5 years again. This is an annual average. And what we see is that for aerosol optical depth, diamond and aluminum are very similar in their distribution. We get this distribution because we are injecting in this area, and the transport of the aerosol will lead to this type of distribution. Diamond has a much higher stratospheric aerosol optical depth, which is because we have more mass. But we also do expect that through higher extinction, which is shown here, the 500 nanometer wavelengths. So we can see how these aerosols differ. And we do run our ME calculation within our model, and we can then, from the parameters we get from the optics from the labs in refractive and in the optical properties, we get these different factors like asymmetry factor, extinction, scattering, and absorption. And that's where you can also start to understand differences between those aerosols and why we choose them for certain things. For instance, the extinction is much larger for diamond, shown here in red. And on the other hand, the absorption of diamond, as well as here calcite, is much lower than the alumina. So this is all important to, on the one hand, understand how much scattering we get, but on the other hand, also how much heating we will get in the model. And so we also looked at the heating. And again, what I'm showing, I hope I said that before, is the difference between our aerosol simulation minus the baseline, no injections. And so what we are looking at here is temperature changes. And I also adjust the temperature changes to the aluminum burden. So we kind of, because we have much more diamond, obviously we would get more mass and more heating, but I adjusted that number so we can easier compare those. We do get the strongest heating for alumina, and that was shown in the previous slide. We do have the largest absorption in the short waves. Then calcite is somewhat smaller. Diamond is actually relatively not that much smaller, but diamond is more effective in terms of radiative forcing. This is consistent with what also Sandro has shown in his study. What we do want to caution here, though, this is only 3 years, so really the results shouldn't be taken they should be only taken qualitatively at this point, since we have to run many more years to compare this statistically. But it shows that we are kind of getting an interesting, we go in the right direction, the implementation seems to work. We also look at radiative forcing, and in principle, this compares again the changes on top of the atmosphere imbalance here, long wave and short wave components. And that compares also here to what Sandra had done for similar studies. What you can see is that our short wave component is a little less than what they found. And especially for diamond, because diamond goes down to minus something 2.3 or so, and we are not even as -1 watts per square meter. But again, this is only 3 years, so that could be a problem. The other thing is that we see that we are just growing more, we're coagulating more. So I'm really excited to discuss this with the group in the breaks and stuff, these results. So again, this is very preliminary in findings. So, and then I want to switch over now to our implementation on the heterogeneous chemistry, because as I said before we had just treated the aerosols and not interacting with the sulfur or the sulfate around, but now we do allow condensation of alumina, and we actually apply what Sandra has done, a approach, which is the contact angle calculation, to consider how much surface area density is actually covered depending on where you are. And so this is very important for heterogeneous chemistry, because heterogeneous chemistry reacts on the surface of a particle. And if the particle is coated with sulfate, then it basically reacts like sulfate. And the heterogeneous chemistry for sulfate is well known. We have it in our model. And some of the more important reactions is the N2O5, the hydrolysis of N2O5, which will change ozone actually and increase ozone in the tropics. But then the other reaction are more important for the high latitudes for sulfate, but then also, of course, for alumina. And so the question really is, how much do we react? And for this heterogeneous reaction on top of alumina, we could really change and create ozones depending on what the uptake rates are. And so this is included in our next simulation. And these simulations are, again, 5 years, but we run it with nudged meteorology. So we're not looking at the heating at the moment. We just want to look at chemistry, how much does it change, and not have that change in dynamics at the moment. And so we run 3 different simulations. And for all of these 3 simulations, we consider different heterogeneous uptake reactions, which is based on the gamma value. And Sandro had developed in his paper a function that is based on different factors, and depending on how dissociative the material would be, the alumina, since they are large uncertainties, and also depending on what components would actually dissociate on the alumina. So one of our experiments is highest ozone loss assumption. That means alumina would be non-dissociative, and that means we have a very high gamma value, a lot of reactions. The other is a lower ozone loss. It is dissociative. We assume HCl absorption and some best fit for gamma. And Sandro can talk about that more if you need more details. And the lowest ozone loss is basically that a lot of stuff will dissociate on the material, and we have co-absorption, so we get much lower reaction rates. As a preliminary results, again, I want to point to Sandro's paper here. He compared 3 different materials, and he looks at the total column ozone in % change of those materials, showing this big range of uncertainty. And people may have seen that. What we want to focus on is the alumina here. So his range of uncertainty goes from the lowest, basically, ozone loss calculations that we have performed. to the largest, or I mean, we are still just assuming one size, 240 nanometers. If you look at different sizes, you get even a larger uncertainty. But what we are seeing is that with the same settings, we get very similar magnitude, at least, of the total column ozone loss, which is also, again, well, we're seeing that we're going in the right direction, and we will have time to look now into other effects. Also for the heating earlier, we can look at dynamics changes at the surface, which we haven't done yet at this point. And so the other thing I want to talk about in my next, how many minutes? 5 minutes? Okay, is the box model simulations. Larry had worked on that really quickly. So this is really imagining a box. That is, when you do injection in a box, the atmosphere, basically we inject somewhere and the aerosols stay together. They do some aerosol microphysics, they evolve, and we stay in that box to look at changes. And we can look at various things with this box model. We can look at injection locations, thinking about point injection versus regional injections. How will these size distributions differ? Number of bins can change results. And we also had differences from Sandra's work in assumption on the mobility radius. How much does that matter? So we really can, with this way, identify more optimal strategies for injections, for example. I want to show it here. So what we assumed was two extreme cases, or at least one extreme case. We would inject 5 teragrams in one grid box, basically. A lot of material, which leads to a mass mixing ratio of something 1 to the minus 3. And so what that is shown here is the orange line. We start at day time 0. We inject as a monomer. If we then go in 30 minutes steps here, you can see how the particles grow, and they grow really quickly. This is a number density per agglomerate fraction towards much larger agglomerates. And that would be going away, obviously, from our size distribution that we want. If we inject much lower mixing ratios, and so in a region, then we keep basically all the particles as monomers, or most of them at least, up to 2 days here. So we kind of can play around with what is the optimal mixing ratio with these studies, and that's what we're planning to do to go forward with. Another example was what you talked about, the evolution. This is where we can see this. What if we, for example, change the number of bins? And obviously, if you inject a lot in one point, you get a lot of coagulation. And you want to basically have a size distribution that covers further than, your size distribution, if you only have 10 bins, then all the material will end up in the largest bin at the end and will be quite unrealistic. So it's important to keep that in mind. For alumina, we're not injecting that much in one grid box. But for example, for diamond, as we see that particles evolve to larger agglomerates, we may have to be careful in what bin structure we want to use. And I'm not sure if I have not enough time for this. This is also, I don't see, oh, there's the timer. Okay, yeah. I want to go, though, to one last study that is really what Crazy is doing, which is the dynamical downscaling, which is now changing gears. We do have stratospheric aerosol injection studies with sulfate, and we have model results for present day and future. But many impact studies have to use really that 100-kilometer grid. And what we want to do is do some downscaling that is much easier for impact analysis. And so we can use our CSM model to apply something that's called dynamical downscaling, which is not just basically interpolating to finer scale, but we really use the model to simulate what is happening in the atmosphere. And Crazy is working on this. And I cannot go too much detail, but if you're interested, and that's why I'm highlighting it, would be great to talk to him more. And I think for future meetings, we can go much more into the detail. So as a really quick summary, we think that we are doing well in implementing the solid materials in CSM at this point. I think we get initial reasonable results in the right direction, a lot to look at. And we're moving this whole implementation now to the next model version, which will allow us to also participate in CMIP7 model simulation. There's an extra hurdle that we have to do now. But in any case, we will then continue looking, once we have moved the model into the newest version, also into the effects on cirrus clouds, which is led by Christina. We want to also do things like tropical refinement of aerosols. This is all big topics, which I just summarized in one sentence here, just for people to see what is coming. But one thing that is important for this meeting is we do want to collaborate, or we already collaborate with the SOCO team and the ITM ESM team to set up a multimodal comparison experiment that we can all do the same experiment and compare what, like Romeric has shown earlier, to say how can we compare the models, why are they different, and so on. And so continued work will happen on the box model. There's a lot of things we can do to understand what is happening. And finally, Crazy's work is something we're further working on, and also especially in collaboration with Romeric's team that we have seen earlier. We do invite some of his team to NCAR in summer to participate in tutorials and trainings, so we're excited about that. And I guess I'm out of time. Thank you.